In this video, we are going to continue our very brief survey of eigenvectors and eigenvalues from linear algebra. Today, we're going to focus on the case of eigenvalues that are complex and how to find eigenvectors corresponding to complex eigenvalues. Once again, we are building up some skills that we will be able to use to help us to solve systems of ODEs using linear algebra techniques. Now, the first thing that I would like to talk about is a piece of terminology that's associated with complex numbers. A complex number, a plus b times I, has a sort of twin, has a sort of brother called the conjugate of the complex number. The conjugate of a complex number z equals a plus bi is traditionally noted by putting a horizontal bar over the complex number. And the conjugate is related to the original complex number by taking the imaginary part, by taking the part next to the imaginary number I and switching the sign. If it was positive, make it negative. If it was negative, make it positive. So, for example, the conjugate of, for example, 3 plus root 5i would be equal to the number 3 minus root 5i. The conjugate of the number 7i, which has a hidden real part of 0, would be the number negative 7i. The conjugate of the complex number 2 minus 3i would be the number 2 plus 3i. The conjugate takes the imaginary part and changes the sign. Let's see how the conjugate appears. Let's go into an exercise and let's try and find the eigenvalues and the eigenvectors of the matrix -2, -7, 1, and 2. In yesterday's video, we found that the eigenvalues of this matrix are complex. One was equal to the positive square root of 3 times I, and the other the negative square root of 3 times I. So the first thing about this that is interesting to me is that these eigenvalues are conjugates of one another. They're the same except the imaginary parts have opposite signs. Let's see if there is any similar relationship between the eigenvectors that are associated with these eigenvalues. Let's start by finding an eigenvector corresponding to lambda 1 equals positive root 3. So I'm going to go into the matrix, and I'm going to take the entries on the diagonal, and I'm going to subtract this eigenvalue. So -2 minus root 3i, -7, 1, and 2 minus root 3i. My task is to find a vector v1 and v2, which when multiplied by this matrix transforms into the 0 vector. Now, do you remember how every single time yesterday when we were finding eigenvectors of a matrix, we really only had to worry about what was happening in this top row? Every single time yesterday when we were finding eigenvectors of a matrix, the top row was the only one that mattered because the second row gave us a redundant equation, an equation that was a scalar multiple of the first. As it turns out, that is happening in this problem as well. In this problem, the second equation is a scalar multiple of the first. The problem is that the scalar multiple is complex valued. the second equation is equal to 2 minus root 3 divided by -7 times the first. And you can confirm that if you want to using complex arithmetic. But I'm going to say that you all can just take that for granted. You can take for granted that when you're trying to find an eigenvector, that the only thing that you need to care about in this class is the top row. So I'm going to take for granted that the second row is redundant, and I'm going to focus on making the top row of this product equal 0. So I'm going to focus on making -2 minus root 3i times v1 plus -7 times v2 equal to 0. Now, just as last time, there is a sort of cheap and easy way to find a vector v1 and v2 that satisfies this equation. And the cheap and easy way is just to force to set v1 to be equal to 1. And then force v2 to compensate. So if v1 is equal to 1, and I plug that back into this equation, that tells me that v2 must satisfy this equation. And solving for v2 implies moving this to the side, dividing by 7 at -2/7 minus root 3/7 I is the corresponding value of v2. And so the eigenvector, going with eigenvalue number 1, is given by I set v1 equal to 1, and then v2 was given by this quantity to compensate. Now let's do a similar thing to find an eigenvector corresponding to the second eigenvalue, -√3 over I, -√3 times I. If I consider -√3 times I, and I go into my matrix, and I subtract that eigenvalue from the diagonal, I get -2 minus -√3i. I get -7. I get 1. And then in the bottom right corner, I get 2 minus -√3i. Which becomes 2 plus √3i, -7, 1 and 2 plus √3i. And I need to find a vector which, when multiplied by this matrix, gets transformed into 0. As always, we're going to focus on the top row, assuming that the second one is redundant. And we find that 2 plus √3i times v1 minus 7 times v2 must be 0. Now, as usual, I'm going to fix v1 to be 1 unit, and I'm going to figure out what v2 must be to compensate. So I have 2 plus √3i equals 7v2, and v2 must be 2 over 7 plus √3 over 7 times I. Whoops, I just caught a typo here, folks. This is supposed to be -2, right? -2 was in the upper left entry of A, so -2 here, -2, -2, and -2. Aha. So having fixed that, we now have our second eigenvector corresponding to our second eigenvalue. v1 is equal to 1, and then -2/7 plus √3/7 I. So altogether, If I looked at eigenvalue number 1, eigenvalue number 1 was positive root 3i, and the corresponding eigenvector, I might call it k1, was 1 negative 2/7 minus root 3 over 7. And then we just found that corresponding to lambda 2, the second eigenvector was almost exactly the same. The only difference was that this time the second eigenvector had a plus sign between the negative 2 over 7 and the root 3 over 7. So something about this strikes me as extremely interesting, because not only are the eigenvalues conjugates, the eigenvectors are actually also conjugates. That turns out to be true in general, that when you have a 2 by 2 matrix with complex eigenvalues, the second one is just the conjugate of the first. And not only that, the second eigenvector is also a conjugate of the first eigenvector. And so what this allows you to do is basically solve the problem in half the usual time. All you have to do is find one eigenvalue and one eigenvector, and then you get the second ones basically for free. All you have to do is change the sign of the imaginary part. So let me show you how I would use that principle in the following exercise. Someone says, please find the eigenvalues and the eigenvectors of the following matrix. So I have 6 minus 1, 5, and 4. I'm going to start by finding the eigenvalues by subtracting an unknown number from the diagonal entries and taking the determinant. And this gives me 6 minus lambda times 4 minus lambda, 5 times minus 1, and after simplification, that looks like lambda squared minus 10 lambda plus, I guess, 29. Now, if I set that equal to 0, that doesn't appear to be factorable. So I'll solve using the quadratic formula. Negative b plus minus the square root of b squared minus 4ac all over 2a. Now, a bit of arithmetic on the side shows that this quantity under the root is equal to negative 16, and therefore the numerator simplifies as plus minus 4i, and therefore our eigenvalues are equal to the conjugates 5 plus 2i and 5 minus 2i. You get one eigenvalue, and the other one comes basically for free, exactly the same, except the sign of the imaginary part is different. Next, I need to find the eigenvectors. But note that I really only need to find one of the two eigenvectors. If I calculate one of them, then I'll be able to get the other one for free. The other one for free by changing the sign of the imaginary part. So I'm going to start by finding the eigenvector corresponding to lambda 1. So I'm going to go into my matrix A, and I'm going to subtract this value of lambda from the diagonal entries. So 6 minus lambda is now 6 minus the quantity 5 plus 2i. Then on the off diagonal, -1 and 5. And then 4 minus 5 plus 2i on the main diagonal. After simplification, this becomes 1 minus 2i, -1, 5, and looks like -1 minus 2i. I seek a vector that becomes 0 when multiplied by this matrix. And as always, I'm going to focus my attention on the top row mainly. So doing matrix multiplication on that top row, I get 1 minus 2i v1, -1 times v2, and if I set v1 equals 1, then that forces v2 to be 1 minus 2i. Now that I've found the first eigenvector corresponding to the first eigenvalue, I claim that we can find the second eigenvector corresponding to the second eigenvalue with no work at all. All I have to do is copy-paste my previous answer, and instead of subtracting 2i, all I have to do is change the sign, and that's it. I'm done. So, when you are finding the eigenvalues and eigenvectors of a matrix and the eigenvalues are complex, then there's usually a bit of extra mental work to do up front. Finding that first eigenvector can be a little bit tricky, but once you've found that first eigenvector, you've got the other one for free. All you've got to do is change the sign of the imaginary part, get the conjugate, and you're finished.